All right, so here's a supplemental video that we actually very much need. I've given you a few heads up in class whenever we actually use this, but let's introduce an important piece of equipment, the DMM. Now, this is a digital multimeter, or as normal people say, a multimeter. You're welcome to laugh at me, but when you drive in your car, you don't call it a speedometer, you call it a speedometer. When you're in a plane, you don't call it an altimeter, you call it an altimeter. So, to me, this is a multimeter. You can laugh all you want. To save trouble and time, and a little bit of my self-worth, we'll just call it a DMM, which is what most people actually call it. Now, the ones we use in class are not top-notch ones. You probably have better ones at home, but they're ones that I want you all to kind of get used to. That being said, on the AP exam, when you're asked to try and set stuff up, feel free to simply use an ammeter, which is usually set up like this. It's called an ammeter. And that measures current. That's one of the things that we've used this for. In fact, it was the first thing that we actually used it for. Or a voltmeter, which measures potential difference, or more colloquially, voltages. Now, this also has a couple of other settings on it too, including something called an ohm meter, which you can actually use to measure things like, well, resistances. They measure ohms. For any of you thinking amperage, voltage, I've never heard of an ohmridge, although maybe we should start that. No, we shouldn't. Ammeter and voltmeter. There are a few things that I want to walk you through on how to use these, the principles that go into them, because they're common things that people overlook. All right, these are going to be important parts of setting up, designing circuits, and specifically experiments in order to test circuits, because normally we need to make measurements of things like the current, which we would do with an ammeter, or the potential difference, which we would do with a voltmeter. Now, these devices that we use in class are actually ones that have both of them built in. Now, there's some upsides and downsides to that. Many physics classes will use just a dedicated ammeter where you don't have to worry about changing settings, and a dedicated voltmeter where you don't have to worry about changing settings on that. One of the reasons why I like using these in classes, these are real-world equipment, and getting used to them can be very useful for you. You'll find these in most shops, among other things, where people are actually using them. They have many different settings. So for the voltmeter, the main one that we're actually using is it will have a capital V with a line and a ... This is what we actually use for regular volts, for our voltmeter. This actually means DC current. There's another one that's actually marked with a capital V and has a squiggly line. This is AC. We don't actually cover that for the purposes of our class, nor is it on the AP exam. So this is the setting. We've got quite a few of them over here that are actually useful for DC voltage or DC circuits, and we're finding the potential difference. AC, we've got a couple settings here. We won't be using them, and we won't really be talking about them for the purposes of this video. However, the same stuff that we have for using a voltmeter regularly is kind of the same thing that you would use for the AC setting. For the ammeter, you would have current, and we use a whole bunch of options over here that is capital A, straight line, and ... underneath it. This is, once again, DC current. I do not see anything on here that is actually marking current for AC. Again, I don't usually do as much with AC because I'm a teacher for DC circuits, and so I'm not specifically a technician, so I'm a little behind on some of that stuff. That being said, let's move forward. All right, here's the key thing. Let's talk about the nature of a circuit. Now, we've started studying circuits in class, and hopefully what we've gotten to is we've realized that if you change the circuit, add things in, it can completely change what you're looking at. If I were to, for instance, remove one of the resistors, it will completely change the total amount of current coming out of the battery because I'm now closing off one of the paths that we have, and it changes the equivalent resistance here, which changes the total resistance of the circuit, which in turn will change the total amount of current coming out. These changes can make huge problems, which means if you don't hook up the equipment right, you might accidentally be changing the circuit. So here's what we really need. if you want to measure the potential across a component, so for instance, if we wanted to measure the potential across the battery, what I would do is I would, well, on the regular DMM in class, we have our common port down here, black cable goes in the bottom, and the red cable is going to go in the middle one for both the voltmeter and for the direct current amps all the way up to about 1 full amp. Technically, it maxes out at 200 milliamp. But what I would do is this. I would then, when I have it set to the proper setting for voltmeter, I can put one lead here and one lead here, and I could measure the difference across those, and it would tell me whatever this value is, the potential difference. It does not tell me if this is at positive or negative or whatever the potential is here. It does not tell me the potential here. It merely tells me the potential difference. And here's the thing. If I put black one here and red one here with the circuit diagram that I've actually got, I would get a positive value. Let's say that I've got 9 volts here. If I've got it like this, I would read positive 9 volts. If I swap these two, I will read negative 9 volts. Basically, the black lead, the common one, is the one that they're saying is, okay, that's the first one, and then the red one is going to be the second. So if I have the first one up high at a high potential and the second one at a low potential, then my delta V, my final minus my initial, small value minus big value, is a negative number. In short, when you're measuring these, if you end up with a negative number, you can kind of reverse them. That being said, with this being the low potential side and this being the high potential, the black one here and the red one here, I would read positive 9 volts. Here's the thing, for voltmeter, you connect them in parallel if you want to connect them correctly. Voltmeters actually have a resistance that goes to infinity. They don't actually have a resistance of infinity, but they have a really high resistance, is the idea. Which means if I put them in parallel like this, in fact, let me draw what this would look like. If I want to put a voltmeter here, I would draw a wire coming off. It would come up to the voltmeter symbol, and then a wire coming in here. This tells me that I have a voltmeter now in parallel with this. Now, this is not shorting the battery. If I put a wire across here, that would be shorting the battery because all the charges could go from the high end down to the low end quickly and easily. You'd be shorting the battery and you would actually shut off the rest of your circuit because the vast majority of the charge is just going to go straight through that wire. This is why it's important that the voltmeter has nearly infinite resistance and is always therefore hooked up in parallel. Since this is infinite resistance, none of the charges really go through here. In real life, you'd have a really tiny amount, but so little that it's not actually changing the circuit by any noticeable amount. I could also measure the potential difference across this. Now, in the AP homework, it talks about the idea of upstream versus downstream, but in short, we've got that this is a high potential. Let's say that, I'm going to throw some reference numbers on here. Let's say that down here is 0 volts, and that makes this positive 9 volts. All of this is actually going to be at positive 9 volts above this point here, 0 volts. If I go across this, the first side is at positive 9 volts. I might find that this side is, let's say, at 6 volts. We have a potential drop. When I do that and I measure across from here, if I do this with the low end here, here's my reference at 9, final red minus initial black, I will read that this is 6 minus 9. I would actually read that this has a potential difference, delta V, properly of negative 3 volts. What we normally do in class is we'll actually just kind of take a positive value, but this is actually what's happening. We start at a high potential, and as we go across this resistor, it reduces some of the energy level. We go from a high value, 9 volts, down to a low value. Positive charges will go from the high value down to the low value. The delta V across this is technically negative 3 volts. That's why if you do set this up, and when you do this in class, something to keep in mind is if you put your black lead on the high end here, and the red lead on the low end, you will actually read -3 volts. Now, what we normally do in class is we take the absolute value of it, or as you may have seen in some of the labs, I tell you, you get a negative number, just flip the leads, because now you have 6 volts on your reference point and 9 volts here. So if my final 9 minus initial, even though that's not actually what we're looking at here, is 6 volts, we'd end up with +3. Normally, we would identify that this has a 3 volt drop across this resistor. In other words, -3 volts. In class, we always use the positive value, but whenever I talk about it, I always say that there is a 3 volt drop across the resistor. This is what I'm talking about. We have 9 volts on this side, 6 volts on the other. Our delta V is technically -3 volts, but we'll usually describe it just as a 3 volt drop. Well, as I continue onward, this might be a little early, but feel free to come back and double check this. We're at 6 volts this entire way. Over here, this is also 6 volts. We end up with 6 volts here and 6 volts here on the high ends of these resistors. Now, with a little bit of loop rule, we know on the far end here, because it connects all the way back over to here to 0, that we have 0 volts here. So if I hook up, don't drop this, if I hook up my red lead here, the far side, and black lead here, I will read -6 volts. If I hook up my red lead here on the high voltage, or high potential, apologize, because this is not a high voltage, this is a high potential. 6 volts is the potential on this side, 0 volts is the potential on this side. The difference between them, delta V, is what is a voltage. This is not a voltage, it is a potential. Delta V, a potential difference, is what a voltage is. The voltage across this is -6 properly, or what we'll actually say is that it has a 6 volt drop across it. It's perfectly fine. If I were to draw a voltmeter across this, it might look like this. I will always draw them in parallel, and this voltmeter is now reading the potential difference across this. I could have a voltmeter here. And it would also read either +6 or -6, depending on how I put them. Technically, the potential difference, because we start at 6 volts and go down here to 0 volts, technically it is -6 volts. You don't have to worry about the negative. In our case in class, we preferentially just keep in mind that resistors will always lower the potential, and so we treat this as a +3 drop, a +6 drop, which is perfectly fine. All right, this is how you use a voltmeter and how you draw them in your circuits. They are always drawn in parallel. They have an infinite resistance, which means you can put them here, but none of the charges are actually going to go through them, so they don't actually change anything about the circuit. You can make a measurement without disrupting the circuit. If I didn't have an infinite resistance, if I had a 0 resistance, for instance, then all the charges would then say, nuts to that, I'm not going through the resistor when I have a nice, easy, no resistance path to go here. In reality, you would have almost all of the current go through here and a very tiny amount through there. Again, we talked about that in class. The idea of path of least resistance doesn't mean that it only goes through one. It actually goes through all of them, but a whole bunch more of it goes through the easier one. This is how you deal with a voltmeter. They're always connected in parallel, and they can be treated as having an infinite resistance. An ideal voltmeter has an infinite resistance. A real voltmeter has a real resistance. It's probably up in the mega ohms, if not more, probably more. We just put a really big resistor in it. All right. When I change the switches, this sets it to voltmeter, which means how I've got it connected in here has a really high resistance. If I switch it over to ammeter, here's where, let's talk about the ammeter, because the ammeter is a little different. The ammeters actually need to be connected in series. And we'll talk about why as soon as I'm done drawing this. Let's say that we have a similar setup here. Ammeters are set up in series. Now, for the voltmeters, they want to compare the potential here and here, so they need to know, they need to be connected here and here, but they're not the battery, so they have to be, since they're connected on both ends of a component, they have to be in parallel, because one of them has to touch one side of the object, and the other has to touch the other side of the object, so it can compare the 2 points. You can't have it simply in line, because if you had a voltmeter here, or built in here, it wouldn't read anything because we have 6 volts here and 6 volts on the other side. It wouldn't see any difference. To get a measurement for the voltmeter, it has to be in parallel so it can look at the 2 sides of the component that you're looking at, be it a battery, be it a resistor, be it a capacitor or an inductor or all sorts of other things. But to measure the difference between this point and this point, it has to be beside it with leads on both sides. All right. For the ammeter, however, here's what we have to do. I want you to think back to what current is. Current is how many charges are going past a given point. Well, one of the easiest ways to count the current, then, is going to be to get those charges, all of the charges that come out of the battery, to go through this meter. And then as it's taking them in, it can go 1, 2, 3, 4, and push them out the other side. The easiest way to count it is to have it go right through the meter itself. That's a great way to think about how and why ammeters need to be set up this way. They need to be put in line with the stuff. They need to be connected in series. The same terminology that we use for resistors also is used for the meters. But, as we know from resistors, if I put something else in the circuit here, if I put a resistor in here, well, that's going to be one more thing that gets difficult for the charges to move through, and it would change the circuit unless we have this act exactly like a wire. Oops, not 0 amp. Bad at this. 0 ohm. When you switch things over to the ammeter setting, they actually have almost no resistance. They get as close to 0 as these devices will allow you to do. Now, they actually have wires in them, which means they're actually going to have a little bit of resistance. But it'll be very, very close to 0, which means when you put them in line, which is what you have to do to measure the current, so all the current will go through the ammeter, it does not actually change things. If you want to put an ammeter in a circuit to measure something, you must put it in series. If it is not in series, it's not going to work right. So for instance, I could find that coming out of the battery, we might have something like 3 amp is what this ammeter is saying. We have 3 amps going through here. That's how much is now going through this resistor, nowhere else for it to go. And we could have it break over here. Over here, I might find that it has 2 amp, and by Kirchhoff's junction rule, we can predict that this will have 1 amp going through it. Back over here, I could put in another ammeter, and it would read 3 amps here. But in each case, I need to connect them in series, in the actual line, so that they can count the charges as they go through. Here's something to think about. Hooking them up right becomes very important. Because if you mess up and you hook up an ammeter like this, it has an effective resistance of 0 ohms. If this is maybe 100 ohms, doesn't really matter what it is. The vast majority of your charges are going to go nuts to that. I'm not going through a difficult resistor. I'm going to take the easy road all the way through this 0 ohm resistance. Now in reality, this won't actually be 0. It'll be a really tiny number. It might be 0.000000001, which means you'd have a tiny little amount of current going through here, but you'd have a whole lot of current going through there. This is shorting out the battery. This is what happens when you basically put a wire across this. You do not ever want to connect an ammeter in parallel because it will actually short out what you're looking at there. And when it tells you the current going through there, that wasn't the current going through that resistor. It's a whole lot more because you've shorted out what you're looking at. For the voltmeter, if you mess up and you connect it in series, like this, congratulations. Remember, voltmeters have a resistance of infinity. or at least it goes to infinity. It's a really, really large resistance, which means you have effectively infinite resistance here. Are you going to have a whole lot coming out of the battery? No. Doesn't actually matter what this thing is. You're not going to have much coming out of the battery because this is basically a brick wall that you've set up. You might as well just have an open circuit. Setting up a voltmeter in series will actually pretty much disable your circuit. This is why it's important to remember. Key things about meter usage. If you want to measure with a voltmeter, you need to hook them up in parallel, and they will tell you the potential difference between the 2 points where the leads are connected. And functionally, they are set to have a resistance that's effectively infinite. Ammeters must always be connected in series, and they will have a resistance of effectively 0. Never hook up an ammeter in parallel, and never hook up a voltmeter in series, because they won't tell you what you want, they'll change the circuit, and they may even damage something at the same time. This is double plus ungood. Very, very bad. The final thing about voltmeters, the nice thing about them is you can actually check things pretty quickly and easily. Let's say that I have a potential drop. Say that this is positive 9 volts, and I have a potential drop of 3 volts, of, let's go with 2 volts and 2 volts. Because those are in parallel, they must have the same drop, and then that would be 5, so this would be a potential drop of 4 volts. Now, if I hook them up with the black lead here and the red lead here going in the regular way that the current is actually going, this would technically read -3. That's why I'm saying it's a drop. This ties with how we've been covering it in class. I'm treating it as the positive, but I know that it's actually decreasing. If I wanted to find the potential difference between here and here, I could connect a voltmeter like this. I don't have to do a voltmeter just across one component. I can actually measure from any 2 points. And from here, I would measure a potential difference of 3 and 2. This would be a potential difference of 5. Delta V would be 5 volts, technically drop, if I put the black lead here and the red lead here, I would actually get -5. I'd get +5 if I reverse those, but the important thing is we know that this is the high potential side, this is the low potential side. If I did a measurement between, let's go from here over to here. It's not the correct color, but let's say that I set up a potential measurement there, potential difference. Well, this would be 2 volts that I drop here and 4 volts that I drop here. I would find that we would have a drop of 6 volts. This is how we can measure the potential difference from several different points in a circuit. But you'll notice, I'm always connecting it where one lead is touching here, one lead is touching here. This is connected in parallel. This is connected in parallel, never in series. All right, that's a bit about using meters to measure circuit values.